So as an alternative to propositional logic, we have first-order logic, which is another kind of logics. That's a more powerful language that develops information about objects in a more compact way, and also relationship between these objects. So in this lecture, I will just give you a flavor of what this looks like. If you want to dive into this topic more, I invite you to check chapter 8 and 9 in the book. So what is the syntax of first-order logic? So now we have terms that can be either constant symbols, such as A, 10, or Columbia, variables that are x, y, z, etc. And also we could use functions in terms of, for example, square root of x, sum of 1 and 2, etc. So we are going to make the language richer with constants, with variables, and with functions. So you could see that already that instead of saying square 1 is clean, we could just use a variable to express any square. We're going to talk about atomic formulas that are predicates that apply to terms. For example, brother xy means that x is brother of y, or the element A is on top above the element B. We're going to keep the same connectives: the conjunction, disjunction, implication, double implication, and negation. We're going to be able to use equality, especially that we deal with functions as well. We're going to use what we call quantifiers, and these are very important to express information about all objects or some of the objects. So the connectives, the equality, and the quantifiers can be applied to atomic formulas to create sentences in first-order logic that you call FOL. So for instance, to express in first-order logic that all squares are clean, we can write for all x, if square of x, then clean of x. This means that whenever there is an x that's square, it is clean. To express the fact that there exists some dirty squares, we're going to use the quantifier exist. There exists x, such as square of x, and not clean of x. So it means that there exist some squares that are not clean. Question for you as a homework. Can we now express that some squares have chairs on top? So to give you a hint, we're going to create two variables, one for squares and one for chairs. And you need to put in relationship these two elements, squares and chairs. Note here that for all x, p of x is like writing p of a and p of b and p of c. So yeah, it's like you're enumerating all possible elements that can be x, right? But we keep it general by for all x, p of x. So this is a compact way of representing this big conjunction of elements. Likewise, exist x, p of x is like writing p of a or p of b or p of c, etc. without writing extensively all the elements. When you see not for all x, p of x is like you are doing exist x, not p of x. So you're going to introduce inward this negation. So you transform the for all into exist, and you transform the p of x into a not p of x. So when you say for all x, there exists a y likes xy. So for all elements, there exists a y that such as x likes y, is not like you are writing there exists y for all x likes xy. So be careful with the order of the quantifiers. If they are different, you can't really simply swap them. So here are a few examples using first-order logic to express that, for example, all birds fly. We could write for all x, bird of x, then fly of x. To express that all birds fly actually except penguins, we could write for all x, bird of x, and not penguin of x, then fly of x. If you want to express that every kid likes candy, we're going to write this for all x, kid of x, then likes x candy. So candy in this case is a constant, and we have the likes, which is a predicate with two arguments. The first one is the person or the kid, and the second one is the element that is liked. Some kids like candy. We have to write this as an exist x, kid of x, and likes x candy. To express that brothers are siblings, we write that for all x and y, brothers x and y means or implies that siblings x and y. So here's a more complicated one. One's mother is one's female parent. For all xy, mother of xy is if and only if female of x and parent x and y. With first-order logic, we can also do inference. While it is a little bit more complicated than propositional logic, there are procedures to do inference with a knowledge base of first-order logic formulas. For further reading, I recommend the book Chapter 8 and 9 that describes very well first-order logic and its inference using different techniques. So the aim is to try to reach natural language. So we have expressed different formulas in terms of propositional logic or first-order logic. The expressiveness of first-order logic is powerful and suggests that it is possible to automate the conversion between natural language and logical expression. This is very valuable for different applications, including personal assistants, question answering systems, and communicating with computers in general. That will put actually logical agents in the smart side of the intelligence level in our general intelligence axis. To summarize, logical agents apply inference to a knowledge base to derive new information and make decisions. The basic concepts of logic include syntax, formal structure of sentences, semantics, the truth of the sentences, entailment, necessary truth of one sentence is given another one. Inference is deriving sentences from other sentences. Soundness is derivations that produce only entailed sentences. And completeness, which derivations that can produce all entailed sentences. The 1+ word, as we have seen, requires the ability to represent partial and negated information, reasoned by cases, etc. Forward-backward chaining are linear in time, complete for Horn clauses. Resolution is complete for propositional logic as well. First-order logic is a powerful way also to represent information and has proven actually to be sound and complete when we use the methods that were derived for first-order logic. It is worth mentioning here that building logical agent was a main research area in AI before the mid-90s. Logic is used in AI to represent the word, but also to reason about the word. Logical agent has pros and cons. They are still used in some applications today, but the problem with logical agent is that they don't handle uncertainty, hence the use of probability more and more in AI. It is completely rule-based, which means that it doesn't use any kind of data to model the word, while machine learning addresses this point and uses data to make invention or to make models. It is also hard to model every aspect of the word, so it can become very quickly very overwhelming and tedious to write everything you know about the word, and there is no guarantee that you modeled everything. However, logical agent has the big advantage of being intelligible. The model produced are intelligible, and it's possible to follow any proof using inference to know what's going on, how this inference was made by using these models that are encoded explicitly. So logical agents tend to disappear today and with machine learning and probability-based methods being more used today. However, I think that there is still beauty in them in terms of framework. The propositional logic and first-order logic frameworks are beautiful, and they actually have this intelligible feature that can be combined with other black box models that do not provide explanations of the reason for prediction or for an inference. Today's lecture is dedicated to John McCarthy, who is the member who coined the term artificial intelligence in the 50s. He also invented Lisp, which is one of the main languages that started AI. He also invented time sharing in computer science. John McCarthy won the ACM award along with the Kyoto Prize and also founded literally the logical intelligence system filled with declarative knowledge in his seminal paper, Programs with Common Sense, published in 1959. I invite you to see his biography in this link. I hope you enjoyed this lecture. Thank you for your attention, and see you next time.